Are there any questions before we start today's very exciting topic? Feedback for assignment 2? I have not yet started to look at assignment 2 yet. So I can't give you feedback. The only feedback I can give is there's a large stack of them sitting there waiting for me. It's been quite a hectic week, very hectic. Any other questions? My signals are telling me about another question. Somebody's wondering about next week, what's happening next week. Does anybody have an opinion about what they would like to have happen next week? Revision class? Good. Maybe we're getting a loop of psychic signals. So I was thinking we have a revision lecture on Monday, and we wouldn't have a lecture on Thursday. That was the suggestion. However, another alternative could be, there are lots of alternatives, right? No revision lectures next week is possible, or 2 revision lectures, or 2 regular lectures, 1 regular lecture. No lecture on Monday, but one on Thursday. The one I was thinking of was a revision lecture on Monday, and possibly if people want like a second revision lecture on Thursday, we can do that. Does anybody have any opinions about that? Okay. Try to calm down. Your opinions are, you don't want your opinion to be too forceful, right? So is anybody in favor of a revision lecture on Monday and then no lecture on Thursday? Does that sound reasonable? If you're happy, don't raise your hand.
Maybe we will have a revision class for Monday, and if it is not enough, we will
Continue on Thursday. Yep, that sounds fine. The official master's student representative, very authoritative. I think that sounds fine with me. Is there the third year representative is absent today, so we could have asked the third year student rep. But we will consult with the master's level student rep as the supreme authority on the matter. Okay, good. If you do have questions, concerns, or things like that, you can let me know anytime. Yeah. Yep.
Today I'm talking to you, sorry for this, but is there any probability to change your coursework percentage overall? I just think about it.
What would you change?
For example, you know that the third assignment is not necessary to submit it. But I think that most of our students started. So can you change the percentage of the overall? I'm sorry for my English, but can we change the percentage because we won't submit the third coursework? So the others coursework percentage will be high. So can we change it? I think it should be low. It will be good for us.
So the percentages don't make a difference, I think, because your coursework is 50% of the module, no matter what. So if you submit this coursework 3, your courseworks are still 50% of the module, right? And if you only submit 2, they're 50%. If you submit 3, they're 50%. So the weight of the first 2 increases if you miss assignment 3. Does that answer your question?
Actually, no. If I submit the third coursework, the percentage is first one is 15, second one is 20, the third one is 15 again.
Mm-hmm.
So if I don't submit third coursework, it will be the
that second coursework, the third one gets redistributed to 1 and 2.
Yeah.
Yeah, that's all that happens, and those percentages increase. So I thought I showed this already. Maybe I didn't.
She wants to increase the percentage for first coursework. That's what she.
Yeah, the weight of courseworks 1 and 2 increases. These are the weights, right? If you submit A3, it's 15, 20, 15. If you don't submit A3, it's 22.5, 27.5 is 0. So the A3 gets split in half, and 7.5 points get added here, and 7.5 points get added there.
It would be really high. It's okay.
Okay. It's still like, the totals are 50% in both cases. So you would change that somehow?
She wants to increase the weight for coursework 1.
So yeah, the reason it's this 1 is a little bit lower is because it's a little bit easier than 2. 2 is more difficult, it's more time consuming, so it gets a little bit more weight. It takes more time. But if you decide to do assignment 3, then that changes. The weight goes down, if you know what I mean. So it's 20%, but then if you do assignment 3, that's the idea.
Sorry, if we do A3 and let's say we do A3 just because there's no downside if we have the time, and we end up with a low grade on A3, would you take the higher grade? So we have 2. No, so if you choose to do A3, you've got to stick with what you get.
That's right. That's right.
Cool. So the chance that you mess it up, it does impact. Yeah.
It does impact. If you want me to assess A3, you get the score that I assess you at, so to speak. But the good part of that is you can ask for a research paper and then decide, oh, do I want to try this or not? That's the other part. It's quite a flexible scheme, actually. I don't know how many modules offer this kind of scheme where you can decide whether or not you want to do the coursework. I think that's very unusual. Isn't it very? I think I've never been in that situation before as a student. So it is a positive thing. Yeah. It's Ben, right? Is it Ben?
Me?
Yeah.
Dennis.
I got excited
the
there.
papers?
Excuse me?
When will you send the papers?
I send you the paper when you ask for one.
I've asked you like 2 days before I go to Tjunction Gaps.
Really?
Yeah.
Okay, because I thought I answered everybody's requests. Are you absolutely sure?
Yes, like 2 days ago.
Did you check today?
Yes.
Okay.
Alright.
Something went wrong then.
Alright,
Just ask
I'll
again.
double
Yeah. Any other questions? And everybody knows there's a special video tutorial just for assignment 3. That's very unusual too. Very unusual.
But where's the videos?
It is on the DataVis YouTube channel.
Right.
So there's a pointer to the DataVis YouTube channel right there. Any other questions? Good, good. Exciting times. So today we're going to talk about streak surfaces. It sounds very sophisticated, and it is sophisticated. This is sophisticated. This is not easy. I'll say that without too much hassle. So we're going to talk about streak surfaces, how to construct them, and how to render them, and what they are today. And this is a streak surface video demonstration. You can find a copy of that on the DataVis YouTube channel as well. And there's a paper about it that we cite at the end of the lecture. I have some extra copies of the lecture just in case somebody might be missing this lecture. And I have the attendance registers as well. So this is a continuation of a long lecture, part 3. We talked about stream ribbons and stream tubes and stream surfaces and flow volumes on Monday, right, just to refresh our memories. Then we went over an algorithm for stream surface construction. Right, this is a stream surface. And stream surface is applied to steady state flow, whereas streak surface is applied to unsteady flow. And then we talked about the definitions of streamlines, pathlines, and streaklines as a refresher, and why we might use integral lines. And then we talked about the motivation behind using surfaces instead of curves or lines. Right, some of the advantages of stream surfaces, but the disadvantage is that they're more difficult to construct. Right, and that's the true about streak surfaces as well. Right, and then we talked about the major phases of the stream surface construction algorithm, the seeding, how to handle divergence, how to handle convergence, curvature or rotation, splitting and termination, then talked about enhancements. And there's a copy of the stream surface video on the DataVis YouTube channel as well. Yeah. And now we're going to talk about streak surfaces. So streak surfaces apply to 3D unsteady vector fields. So that means that every position in space, in the 3D space, there's a vector that's changing over time. So sometimes we call that 4D. So already you have a challenge, right? The large amount of data. It's a lot of data. Right, so at every sample position you have at least these 4 data points. They all have a direction, they all have a magnitude, and they all describe the velocity field, the motion of the velocity field. And in our case, since we're talking about unsteady flow fields, it's changing over the time. And these are usually coming from simulations, CFD simulations. Just a little refresher. So streak lines, the curves that are formed by joining all particles passing through the same point in space, right, at different times. That's a streak line. Remember I used the balloon analogy and the dye analogy. So the strong relation to smoke or dye injection from experimental FlowVis. These are images of experimental FlowVis. Right, that's dye being injected into flow. This is a wing, actually, and studying the behavior of air as it passes a wing. Right, a very, very big topic if we want to fly around to different places. So streak surfaces are an extension of streak lines, the next higher dimension. So we don't want a curve, we want a surface. So you can think of the streak surface as being formed by a seeding curve somewhere in the domain, like here, and then injecting dye all along that curve into the flow. In our case, it's not dye, it's a surface that's injected into the flow or integrated along with the flow. Right? It's a massless surface and an infinitely thin surface. You can also imagine just an infinitely thin, massless blanket, infinitely flexible blanket being dropped into flow. That's a streak surface. Right. So the challenge is the computational cost. The surface advection is very expensive. That means the updating of every vertex in the surface, that has to be updated every time step over the entire surface. So the whole surface is dynamic. Every vertex moves at every time step. And that's not true about the stream surface. The stream surface, it's only the front. Same with the path surfaces. Right? So we have, and again, we're trying to develop a streak surface made of quad meshes, or a mesh, and it has to be able to handle divergence, convergence, and shear. So when the flow splits, comes together, and rotates, right? And we want that the surface remains nice and smooth. Right? That's a big challenge. We have to handle critical points. That means areas of zero velocity, or the velocity goes to zero. And we have to have very efficient memory access, right? Because generally you can't just store all the data in main memory at the same time. Can't do that. This was, just on a historical note, this was an unsolved problem for a long time. So Swansea University worked hard on this problem to solve it. And we were one of the first people to ever solve this problem, back in 2000, I think 11, by a very talented student, Swansea University student, Tony McLaughlin, very talented. Yeah, so Tony McLaughlin shocked the world by presenting the world with some of the first streak surfaces in the history of mankind. So the general idea is this: we try. Usually surfaces are composed of triangles. We tried an experiment where the surface is composed of quads, 4-sided polygons rather than 3-sided polygons, and we try to operate on each quad in a way that is reminiscent of the marching cubes algorithm. So the beauty of the marching cubes algorithm is that you can traverse the volume quad by quad or cell by cell, make some updates, generate the surface, and then move on. And that's what the spirit, the same kind of spirit that we have in this. We visit each quad in the mesh, and then we update each quad in the mesh one by one, so to speak. So that lets us swap in some parts of the surface when we need them into memory, and then swap out parts of the surface when we don't need that in memory, right? So local operations for surface refinement, as opposed to trying to update the whole surface at the same time. And so no global optimization is required. That means we don't have to have the whole surface and the whole data set in main memory at the same time. That's what that's about. So it's a CPU-based implementation. We didn't really talk much about CPU versus GPU implementation, so that's not something that we have to be concerned about in this module, right? So let's talk about the complexity. So this is complicated, actually. This is not a simple algorithm and a simple problem and a simple solution. Maybe someday it will be. Maybe somebody will publish a way to do that's simpler, which would be nice. So we have a list of particles. That's our mesh, right? We have a quad mesh, and those are each particle. Those are all particles. So they're massless particles that are sitting in the flow, and they're connected by this mesh, right? The particles form vertices that create a mesh, and the mesh is the surface, right? So we have a list of quads. So this is a quad. This is one of them. This is another one. In this case, it's called QW, which means the west quad. And this is the north quad, and this is the south quad. We store pointers to the vertices. We store pointers to all quad neighbors. So this quad has a pointer to its northeast neighbor, and this quad has a pointer to its southeast neighbor. And we also have these special things called T-junctions. So here are two quads, but their sizes are different than this one. So in order to compensate for that, we need this special object called a T-junction, which is this highlighted here. Right. The T-junctions store extra vertex neighbor information. So this quad knows it has a T-junction on its eastern side, and this T-junction knows that it has a quad on its northern side and southern side. Right? And there's a special arrow here to an extra vertex. There are 3 vertices here. This is what makes the algorithm complicated. This is what makes it complicated. If every quad was exactly the same size, always, it would be much, much easier. But it's the fact that the quads can change sizes that makes it more complicated, and we have to introduce this T-junction, which is really a reconciliation between the high-res and the low-res version of the mesh, or the regions. We also have a special constraint that only one T-junction is allowed per edge. So on this edge, only one T-junction is allowed. So that's a little bit of introduction to the data structures. And there is some similarity with the stream surface construction, by the way. There is overlap there. This is essentially the time-dependent version of stream surfaces in some ways. So there is some overlap. So if you understood the stream surface construction algorithm, that's very good. And that might even help you on the test, for example. So the overall algorithm is we start by seeding a rake. Then we integrate the vertices. That's the same, right, in some ways. That stage is also in the stream surface construction algorithm. We remove terminated vertices and quads. And then we handle divergence, convergence, and shear. And that's also called updating the sampling rate of the mesh. We then handle boundary conditions. And then if we're at the last time step, we exit. If we're not at the last time step, we keep iterating and we update. This is an iterative loop until we get to the last time step in the data. Sometimes we use this term advect, by the way. That's the same thing as integrate. Remember we had a special lecture on streamline integration, how we compute the next point along a streamline given the previous point. It's the same thing. So we advect the surface. In other words, we compute the next step as it gets pushed or transported by the flow. This refined surface means we check the surface to make sure it's still smooth. We test for boundary conditions, update, test for termination criteria, and then render. Looks fun, doesn't it? Imagine if this was assignment 3 to implement this. That would be cool. It took over a year, the first implementation, I believe. So probably won't have that as a coursework. So how do we handle divergence? So imagine the flow is splitting. So somehow that splitting has to be represented in the quad mesh, keeping it smooth. Right? So imagine this is a quad, and we integrate or advect these two vertices, right? And the flow pushes them apart. That's the D set parameter that we always see. if that happens, then the quad gets split in half. And we have two new T-junctions, one along the north side and one along the southern edge. But because all four vertices get updated at every time step, this can happen in any orientation. It doesn't have to just be the downstream orientation. It could be the upstream orientation, and it can be the west and east, or west and east orientation. So it could happen that these two vertices get split apart or get separated. And in that case, the quad gets split or divided in the west-east orientation. And these two new junctions appear. So that's how we handle divergent flow. And divergent flow is the most common case, by the way. Most common one. Right? Convergence is a little bit more complicated. So if we have flow that's coming together, if we don't handle that somehow, reduce the number of vertices, then we'll have these tiny quads and we'll have lots of extra redundant computations that we don't need. Also, the surface won't be smooth anymore. It will get this wrinkled look, actually, from numerical error. So convergence happens when neighboring particles move too close to one another. Right? So imagine we have a quad and these two vertices, we integrate their positions, and then they get very close to one another. And this distance is less than d sep. Right? This distance right here is also less than d sep, so they're both less than d sep, which is the same d sep that we talked about in the streamline seeding algorithm and the stream surface construction algorithm. So in this case, the two quads get merged. These two quads get merged. And look, there were two quads here, there were two quads here. There are still two quads down here, so we have to introduce this T-junction object to make sure that our mesh is nicely sampled. And by the way, there's some notation here. The V stands for vertex, so you can see all the vertices are labeled. And the subscripts are directions. So NW means northwest. V is a vertex, and N means the northern vertex. This is the northeastern vertex, southeast, southwest vertex. It's important to be able to keep track of which vertex is which if you're actually implementing the algorithm. And the same can happen, so this is the north-south orientation. The same thing can happen along the east-west or west-east orientation. Right? A quad could get scrunched this way. That means we just are removing particles from the surface. So we merge the quads with their neighbors. And the configurations generally fall into these three cases. So this is a quad being merged. This is what the configuration looks like afterwards. The mesh configuration, so there are two new T-junctions. This is the case when a quad is merged. And then there are two here and only one here. So we only have to introduce one new T-junction. And this is the same when these quads get merged, but this one is at the top, or the north side of the quad. So it's really the same as this. It's not really different. It's symmetric. Does that make sense? It is pretty intuitive, actually. It's just tricky to implement. It's tricky to implement this because of the T-junctions. But I think splitting quads and merging quads is quite intuitive. Right? It's not a big shock. Shear is how to update shear is not so intuitive. Right? When the flow is twisting or rotating, we can get a very deformed mesh. Right? And the deformities in the mesh can lead to a low quality surface. You can see, for example, the distance between these vertices increasing, and if that distance gets too great, then you start to see folds in the surface, and the surface doesn't tight. The surface no longer accurately represents the underlying flow characteristics. So these are two cases of handling shear, right? One involves 1, 2, 3, 4, 5 quads, and one involves just 1, 2, 3, 4 quads. Right? There are two different cases. Right? In this case, this quad, this edge gets updated down here, so it actually gets repositioned here. So this edge is repositioned here, over here. And that's how we handle. So you can see how this is a quad that's been sheared quite a bit. And now it's still sheared along the southern edge, but it looks more like a square on the right half, on the right side. Okay? And when we handle the shear operation again for the southern neighbor, this one will get moved down too. This is the case when we have 1, 2, 3, 4 vertices at 4 quads, right? This edge, this is the quad that we're applying the shear operation to. This edge gets reconnected down here, so it went from here down to here, so it's more of a quadrilateral shape, right? And if you look at the blue edges, those are associated with T-junctions, so they're highlighting the T-junctions, right? So this T-junction, there used to be a T-junction here, and now it got moved up here. Here, this is nice because it's the equivalent of two T-junctions merging, so they disappear. The fewer T-junctions we have, the nicer it is. And the other part I didn't mention is how to detect the shear. So we test the ratio between the quad diagonals. This is showing the ratio or the two quad diagonals. That's how we test for this case. If we have a perfect square, then the ratio of these two diagonals will be 1. They'll be the same length. Like length divided by itself is 1. But if the quad becomes too sheared or too elongated along one of its axes, that ratio is less than, can be less than 1. So if we divide, for example, the short edge by the long edge, and we find, oh, that's less than half, we know, oh, this quad has been sheared, and we need to update the vertices. So, in fact, it just means updating the mesh connectivity, right? The new quads are not created, and quads don't disappear. The only thing that happens is that the connectivity, or the edges, the connections are get updated. That's the tricky bit, by the way. Very tricky. And here's another tricky aspect about the T-junctions. Right, if we have a quad like this and we have a T-junction here, right, there's a vertex at each T-junction, there can be gaps that appear. Right, this vertex might get vectored this way, this vertex might be integrated that way, this vertex might get integrated that way, and there could be a gap that appears along the edges of the quad. So to handle that, instead of rendering, for example, a quad and then 2 triangles, which we could do, we turn this into a triangle fan 1, 2, 3, 4, 5. And that gives us a smooth surface without any holes, right? And this is actually one of the reasons we store the T-junctions as their own objects, right? So we store the T-junctions as their own objects, and they don't necessarily lie on these edges. They can drift off. They can drift away through when the surface is integrated and updated. And if we don't handle that somehow, then we'll see cracks appearing in the surface, right? And this would appear as a crack, right? So instead of rendering holes and cracks, we want a smooth surface, so we transform this into a triangle fan. And then we get a nice smooth surface. It's a lot of information today. So now when we look at this, we can see what's happening in a little bit more detail, or we can understand what's happening. So all those things are happening at every time step in this video. So these are all quads, and their positions are being updated at every time step. Some of the quads are diverging, some of the quads are converging, and some of them are rotating. In this particular case, there's not very much rotation in the downstream direction of the flow, but the rotation starts to come at the end in the orthogonal to the downstream flow direction. Right, and this also shows the terminating conditions, by the way. So when it reaches the boundary, the quads are removed from the surface, and you can see the surface can split into pieces, right? Because one piece can hit the edge, the boundary edge, and then cut it into different pieces. Does anybody know what color is reflecting in this video? What color is mapped to? Where's the attendance? Anybody want to take a guess what color is mapped to? Intensity? Close. There's another, maybe the word you're looking for is velocity magnitude. So velocity magnitude. So slow flow is mapped to the color at the bottom, and fast flow is mapped to the color at the top. Which I guess that's probably what you meant, isn't it? Intensity.
Number of quads.
So the number of quads is changing. Yes, it's always changing. What's missing, there is something missing from this video. And I think it just came into your head. What we didn't produce is a video that shows the mesh only. It would be nice to see the mesh without the polygons, just to see the edges, to see what the edges look like. We do show that in the stream surface video, but we never see it in the streak surface video. But if we could see only the edges, we would see all those things happening. So here you can see the splitting, for example, and here you can see the convergence. But you don't see it explicitly in the mesh because you can't see the mesh right now. And one thing we didn't mention is the performance time. So this algorithm can run pretty quickly, so we can get something like 2 to 5 frames per second. So this was the first fast streak surface algorithm. And Sally looks more interesting when she's time dependent. Well, it's kind of more engaging because Sally's alive. She's not a mannequin. You can see the quad mesh from the stream surface example in the stream surface video, but you never get to see it in the streak surface video. There is another big topic that we didn't mention. Anybody want to guess one of the topics we left out? We leave out kind of a lot of topics, but there's one that's really kind of staring at you in the face about what we left out. Anybody want to take a guess? We never talked about the seeding. We talked about streamline seeding, but we never talked about the other seeding, things like stream surface seeding, right, and pathline seeding, and all those things, and streak lines, streak surface seeding. So if anybody finds this kind of interesting, there is no streak surface seeding algorithm in existence yet. No automatic one. So somebody's going to do it first. The first time I gave this lecture, there was no stream surface seeding algorithm, really a fully automatic one. And then Matt Edmonds came along and shocked the world and produced some of the first automatic stream surface seeding algorithms, which are very well known throughout the world today, just a few years ago. Okay, so one of the ideas that we're trying to convey is that surfaces offer advantages over curves in certain cases, right? It can offer nice visualizations of flow that curves can't, right? And we presented interactive algorithms for the construction of stream and path and streak surfaces. And they're all based on local operations performed on quad primitives, right? The meshes are quads, and they handle divergence, convergence, and shear flow. They handle topological changes or splitting, right? And they're demonstrated on a variety of data sets. And if you're interested in seeing more details about these things, these would be 2 very good candidate papers for assignment 3, by the way. So those would be 2 samples if you're wondering about assignment 3, what the papers might look like. Then that's something like what they would look like. And that's a photo of Tony. He dresses like that every day. That's just what he looks like. Any questions, comments, concerns? Okay, I guess we'll end there then. If anybody's curious, there are some examples of the stream surface seeding algorithms on the DataVis YouTube channel if you want to see what that looks like. But you'll not find any streak surface seeding videos in the world. If you do find one, please let me know. But I don't think they exist yet. Okay, happy Thursday, Friday Eve. Happy Friday Eve.